I'm taking a 1 hour extra session just to summarize the concepts that we have discussed in the tutorials or that you have seen in the lectures. Uh, so let's just go through the concepts, and if you have any doubts, you can ask me in between or also at the end. Right? So you must have come across this concept that entropy is treated as two parts. So we usually write entropy as a reversible part and an irreversible part, right? So the reversible part is whenever you are adding heat to the system or removing heat from the system, then we treat it as this process which you know what is happening, right? And DSI is the irreversibility, which is always going to be positive. So as you can see, it is written here that DSC can be positive or negative depending on whether heat is being added or removed from the system, but DSI, that represents the irreversibilities and it is always positive. Okay, so the next concept that we saw was the stagnation concept. Do you remember how the stagnation state is achieved? Can one of you please answer? Okay, adiabatically is enough. Yeah, and reversibly also, right? So it has to be a reversible and adiabatic process from which, so starting from a static condition, if I use a reversible adiabatic process and go to what condition? What does stagnation condition mean? What is the Mach number at that stagnation condition? 0. Yeah. So you have to basically become stagnant, right? So you have to go to Mach 0. And this is the reference state which we use to solve isentropic flows, right? And a very important point was that whatever frame of reference you use, the static conditions are going to remain the same, but the stagnation conditions will change depending on what frame of reference you are using. Because you can see here that the stagnation enthalpy is equal to what? The static enthalpy plus V square by 2, right? Just ignore this. This is a normalization constant used in the textbook that I was referring. Okay, so you can see that V is the velocity, and depending on what frame of reference you have, your stagnation enthalpy is going to change. Is this clear? Okay, and we have also seen the energy equation, right? So energy equation we write as the total enthalpy plus any heat added will be equal to the total enthalpy at state 2 plus the work that is produced by the system. Okay, and then we say that if there is no heat added or removed and if there is no work done on the system, then the stagnation enthalpy is going to remain constant, right? So these conditions are very important, and if these conditions are satisfied in any flow, we are going to treat the stagnation enthalpy as constant. So can you give me some examples where the stagnation enthalpy does not change? We have studied a lot of flows. Yeah, normal shock. Okay. So in a normal shock, stagnation enthalpy doesn't change. What about stagnation pressure? Yeah, the stagnation pressure reduces. And why is that so? Yeah, it is due to the irreversibility. So we also saw this stagnation pressure energy equation somewhere in the tutorials. I just wanted you to know that there exists this equation which says that your stagnation pressure, okay, this is the term which relates the stagnation pressure to the entropies. Alright, so obviously we have assumed that there is no work being added, there is no heat process, heat exchange, so let's get this also to 0. So whatever stagnation pressure changes happen in such systems, they will be due to the irreversibilities, and if there is no irreversibility, only only then stagnation pressure is going to remain constant. So what is one example where stagnation pressure remains constant? One example where stagnation pressure remains constant. In a CD nozzle, right, if it is operating at the first critical or third critical, will the stagnation pressure remain constant? Yeah, anyone can answer, please. Yeah, in isentropic processes, right? So one example is a CD nozzle operating at first or third critical. Okay, I hope you remember the first and third critical points. Okay, yeah, okay, so here's a question for you all. We've already seen the concepts, so it is simple to answer. One can either use the frame of reference of person A or person B, and in either case you have to tell which of these statements is correct. So the stagnation pressure is the same as measured by person A and person B. Is this true? Or is the static pressure same for person A and person B? So person A is standing, but person B is running it. He has some velocity. Which of these options is correct, or none of them are correct? Option A is wrong. Okay. Yeah. And what about option B? Yeah, B is correct. Right. So static pressure or any static quantity for that matter, it does not change whatever is your frame of reference. Okay. So here's another question. Consider the case of a steady one-dimensional flow with one stream in and one stream out of the control volume. Okay. Under what conditions can we say that the stagnation enthalpy remains constant? We just saw above. We saw the stagnation enthalpy, the energy equation, right? So when will the stagnation enthalpy remain same? Okay, Q is 0, no heat added, and work also 0, right? And again, so we also saw that the stagnation pressure can actually change under these conditions, and the only case where stagnation pressure will not change, so in addition to Q equal to 0, W equal to 0, we need to also have losses equal to 0. Okay, and then we also saw this equation. So do you remember the relation between the stagnation pressures and entropy? So what this equation says is that if there is a change in the entropy, say for example due to losses, and like we saw in the very first equation, ds, which is dse plus dsi, and if dse is 0 and dsi is always positive, then I know that in this equation delta s is positive. So e power minus delta s by r is going to be less than 1, which implies that if there are losses in the system, I should expect that PT2 should be less than PT1. Right? Okay. So that means stagnation pressure will drop whenever there are losses. Okay. And you must be familiar with these equations. How is the sonic velocity defined, and what is the Mach angle, Mach number? Right. Okay. Okay, and we have also seen these special relations for perfect gases. And when are these equations valid? Are they valid for any flow? Are these only isentropic relations? Can they be valid only in isentropic flows? Now, what are the me a formula for the stagnation enthalpy or stagnation temperature in terms of the static quantity and the Mach number, right? So does the flow have to be essentially isentropic? Anyone? Okay, just give me a yes or no. It's okay to be wrong. Yeah, my question is that I have given you these equations. Can I use these equations only in isentropic flow, or can I also use them in non-isentropic flow? Okay, can I define the stagnation temperature with this formula also in flows which have shocks? How do you define stagnation temperature when there's a shock? Okay, so remember we said that the stagnation quantities are defined such that you start from the static conditions, whatever condition your flow actually is at, and then with a reversible isentropic process you move to Mach 0, right? So this is an imaginary process, and this is just a reference state, stagnation enthalpy or stagnation temperature. So I can always have a flow with a shock, right? And in region 1 or in region 2, in either cases I know the static quantities, and from here I can go to the stagnation state for 1 and also the stagnation state for 2, isn't it? So these equations are valid even for non-isentropic flows. It's just an imaginary process. Do you understand this? Any doubts? Repeat what? Yeah, why we can use it anywhere. Okay, so how did we get this equation? So let's go back. We derived the energy equation, okay, and in the energy equation we said, okay, put Q equal to 0, W equal to 0. So that gives me that the stagnation enthalpy is constant. But right now I am not applying any conservation equation like energy equation or something. I am just defining a new state, which is the stagnation concept. So when we got this definition, remember the stagnation enthalpy is static enthalpy plus V square by 2. So if you rewrite this, you just have to rearrange and then you get this equation which I have shown you here, right? So what this tells me is stagnation enthalpy can be related to the static quantity and the Mach number. So I can use this in any flow, right? What was stagnation reference state? You start from some point, okay, yeah, so this is the let's say this is the HS diagram, okay, and this was your original state, okay. So let us say this is the state 1, and from here you have to go through an isentropic process, reversible adiabatic process, to a state 1s, or okay, in this case it's written as T, and this I can do for any state 1, right? And let's say I have a normal shock, and after the normal shock I have some other condition 2, okay. Then from 2 also I can go through an isentropic process and I can reach this point 2T, and they will be at the same enthalpy line, because in both the cases 1T or 2T I am reaching Mach equal to 0, right? Okay, so let us see this question. Consider a steady one-dimensional flow for a perfect gas, and okay, I don't have the figure here, but okay, the TS diagram shows both static and stagnation points at 2 locations in the system. It is known, okay, let me just check the figure. Give me a minute. Okay, somehow I forgot to add the figure. Just hold on. Okay, anyways, let us come back to this question a little later. Okay, I got it. Yeah. Um, no, I think I got the figure. Yeah, it's okay. Okay, let me start presenting the screen again. Just a second. Okay, can you see the screen now? Yeah, okay, so now you can answer the question. So, is the heat transferred into or out of the system? How do you say this? Yeah, please answer. So, you can see there is this, yes, into the system. How do you say so? Right, so the temperature has increased. If you compare point 2 and point 1, so are you comparing the static points or the stagnation points? Yeah, you should compare the stagnation points. That's very important. Okay, so yeah, here the answer is into. Yeah, so you should ideally compare these lines. You should not compare 1 and 2. Can you tell me why? Yeah, yeah, or another way of seeing this is, so you have this case, right, ht2 plus w. Now it is possible that heat is actually being removed but work is being done on the system, so that also might change the temperature states in a different way. And we also saw Rayleigh flow where the velocity was changing in so we had a, okay, we'll come to that, but if you remember, in Rayleigh flow there is a state of maximum entropy and there is a state of maximum enthalpy, right? So between the maximum enthalpy and maximum entropy state, the temperature actually reduces despite adding heat to the system, right? So you can only see the stagnation quantities and infer whether the heat is being transferred into or out of the system. All right. Okay, so what about question B? Is M2 greater than M1, equal to or less than M1? Why? A equals, no, it is, no, just think again. See, the static points that are given to you, from them, okay, for both these static conditions, this rise A and this rise B is given to be the same. How can the Mach number be same? Okay, you said the right thing, but think a little more. What is Mach number? What did you say? Because A is equal to B, what does that imply? Yeah, kinetic energy will be same, which means velocity is going to be same. So how can you conclude the Mach number? What is Mach number? Right. Yes, m2 will be lesser than m1 because t2 is more than t1. Right? So velocity is same but not the Mach number. So be careful. Alright? Okay. Okay, so let's move on to this next set of questions. You have to state whether these questions are true or false. Right? So changing the frame of reference does not change the static enthalpy. Is that right? True or false? Why? Okay, we just saw that stagnation enthalpy depends on the frame of reference, not the static enthalpy. See, whether I'm moving in a train or whether I'm sitting at my home, the temperature that I feel is going to be the same, isn't it? Yeah. So this is true. What about the part B question? Shock waves travel at sonic velocity through a medium. What are shock waves? The normal shocks that we have seen, right? Yeah, and we have also solved questions on moving shock waves. So do they travel necessarily at sonic velocity through a medium? Okay, come on, take a guess, true or false. Yeah, false, right? Because it's a any supersonic flow. So if Mach is more than 1, then the waves are going to travel at velocities which are higher than the sonic velocity, right? Okay, so in general, one can say that flow losses will show up as a decrease in stagnation enthalpy. Is this true? Stagnation pressure, not enthalpy, right? Okay, the stagnation process is one of constant entropy. Is that right? How are you achieving the stagnation state? It has to be constant entropy process, right? And reversible as well, right? Okay, so a Mach cone does not exist for a subsonic flow. Is this true? Is it true or false? Why? What is a Mach cone? Right. So for subsonic flow, does it exist? So this is true, right? It does not exist as written. Okay. Okay. So let's move on to the next part. So if you remember, we've done these area Mach relations when area is varying in the duct, right? So using these equations, you can tell me if area is decreasing and Mach number is less than 1, what is going to happen to the pressure and velocity? So we are talking about subsonic flow here. Right, so pressure is going to decrease and velocity is going to increase. So what is this going to be, a nozzle or a diffuser? Nozzle, right. And when the area is increasing for subsonic flow, then it is a diffuser, right? Okay, and for supersonic flow, it's the opposite. So when the area is increasing, you can see that velocity is going to increase. Right. So yeah, so we have the nozzles and diffusers for subsonic and supersonic flow. Okay, Now there is another reference state that we have studied, which is called the star reference state. And how did we achieve the star reference state? It is similar to the stagnation state, because see, you start from whatever point you are at, and then you achieve a state by a reversible isentropic imaginary process, and you achieve Mach equal to 1. In stagnation, again it's reversible isentropic, but you achieve Mach equal to 0. And here it's reversible isentropic, but you achieve Mach equal to 1. So I hope you understand what is a star reference state. Alright, now if I start from two different static conditions, will the star reference state be same or different? Different, yeah, say it confidently. So this is important. We'll come back to this when we see Rayleigh and Fano flow. So you will see that for Rayleigh and Fano flow, the way you define the star reference state, it is going to be same no matter what initial condition you start with. Okay, so in this question, in the TS diagram which is given, point 1 represents a stagnation condition. Proceeding isentropically from 1, the flow reaches a Mach number of unity at 1 star. Point 2 represents another stagnation point in the same flow system. Now assuming that the fluid is a perfect gas, you have to locate the corresponding isentropic 2 star and also prove that T2 star is either greater than, equal to, or less than T1 star. Like, you have to tell me whether T2 star I should mark it above this line or below or at the same point. So how do you do this question? Did you understand the question? So we just now discussed, if we start at two different static states and then we achieve the star reference state, you said that the star reference states are going to be different, right? So we know that T2 star is definitely not equal to T1 star. So this we have already established. So now the question is whether it's greater than or less than. Why? How? Okay, first of all, you are saying greater than. So let's say it's here, right? So should I mark 2 star over here, here, or here? A, B, or C? Right. Yeah, so it has to be isentropic, so it has to be a straight line like this, right? So definitely it's B. So now the question is, you said T2 star should be more than T1 star. Why? Yeah, go on. Who answered it? Just tell me what is your reasoning. Sorry, I did not get you. Can you repeat? Stagnation temperature is? Right, so the initially, yeah, so these are stagnation conditions. Again, I could not hear you clearly. You're saying that T02 is greater than T01, and that is why T2 star is greater than T1 star. Yeah, right. Yeah, that is correct. Okay. Any questions about this, or should I move on? Okay. Yeah, thanks. So we saw the conditions for standing normal shock, and these are the equations we have derived. So this is from the continuity equation, then energy equation, and the momentum equation. Right. So what do we understand? What are the quantities that are conserved across a normal shock? What are the, yeah, T naught H naught is okay, essentially the same thing, fine. And what else? Yeah, so stagnation temperature or stagnation enthalpy, H naught remains same. What about P naught? P naught decreases, okay, so P naught doesn't remain same. Yeah. And what else remains same across a normal shock? You can see the equations here. Yeah, go on. So how do you derive the continuity equation? You say that the mass flow rate is going to remain same, isn't it? Yeah, so the mass flow rate remains same, mass conservation, and then you have this P plus rho V square. This quantity remains the same. Okay. You can see that is how you would have derived this third last equation. So this is constant across a shock. Alright. Then we also saw CD nozzles, and this is the diagram that we've discussed several times. So can you tell me what is the Venturi regime? What happens in the Venturi regime? And if a CD nozzle is operating in the Venturi regime, which gas tables would you use, or which equations would you use? Come on, we've solved questions with this. Anyone answers? Yeah, it's a subsonic regime. So the flow is going to remain subsonic in the converging and the diverging part of the nozzle. And which equations would you use, or which gas table would you refer to? Isentropic gas tables, right? And what happens at the first critical? What happens in the nozzle? In the first critical situation, will a shock be formed? What is so will you use the shock tables to solve the first critical, or the isentropic table? So what is first critical? We say that in the converging section, the flow is subsonic. It reaches exactly the sonic speed in the throat, but despite that, it remains subsonic in the diverging section, isn't it? So there is no shock over here. Even at the first critical, you will use the isentropic table, right? And then comes the third critical. So how do you define the third critical? Completely supersonic. So do you mean that even in the converging section, but is it possible that I have a subsonic flow to start with, and no, really, do you have supersonic flow in the converging section? Right, supersonic flow at the exit, that is fine, but I will get a supersonic flow even otherwise. Yeah, it is a shock-free flow throughout the nozzle. And can you tell me what is in the converging section, subsonic or supersonic flow? Yeah, it is subsonic. Okay, so how do you remember this entire chart? See, on the left hand side, you can see what you've plotted is the pressure ratio, right? And what this pressure ratio tells you is, in a physical system, what you can change is either you can change the pressure here, which is the chamber pressure, or you can change the pressure here at the receiver end. Okay, now let us say I'm using this receiver pressure and I have fixed my pressure ratio at this point. Then I have ensured that the flow is going to be subsonic throughout. As I keep decreasing the pressure, the flow conditions are going to change. Why is this happening? Why does a shock even occur? Or why do we get supersonic flow? Because the flow is forced to behave in a certain manner depending on what pressures you have applied across the CD nozzle, right? So now when you decrease the receiver pressure starting from this point, you cannot immediately come to the third critical. If you are eventually decreasing, you will first get shocks at different locations. Is this concept clear? Alright, so that is why you should remember, see, first you started with the Venturi regime. Anyways, the flow was subsonic in the converging section. And then you went beyond the first critical, which is where you start getting shocks. But the flow is still subsonic in the converging section. Okay, so don't get confused about that. Alright, and can you tell me what is the second critical condition? So we have the first critical condition where the flow remains subsonic throughout the CD nozzle. Third critical, where we have supersonic flow in the diverging section, and what is most important is that it is isentropic. Okay, now can you describe the second critical? It's written here, shock at exit, but can you describe more? What can I say about the flow inside the CD nozzle? Just before the shock. Yeah. Yeah. Right. Right. So I can say that, okay, at the second critical, I can say that the flow throughout the CD nozzle is actually isentropic till just before the shock, isn't it? Yeah. Okay. Okay. And what do we have between the second critical and third critical? Over expansion. What does that mean? What is over? Yeah. Okay. And what will happen due to over expansion? So you are saying that, okay, what you are saying is, if I have placed my receiver pressure somewhere here, the pressure that is actually achieved at the exit pressure is, compared to the receiver pressure, it is more than or less than? Less than. So what will happen? How will the flow adjust itself so that the pressures become equal? Right, oblique shocks will be formed. Right, and similarly for under expansion, what is going to happen? Yeah, expansion fan will be formed, and we can say that PE is actually more than PR. Yeah. Okay, so I think the most important takeaway point is that these pressures or the pressure ratio is the control parameter. So practically, if you have to create any of these flows, you should know how to control the pressures. Alright. Okay, so let's answer these questions. You have to fill in the following blanks with increases, decreases, or remains constant. So what happens across standing normal shock for the temperature? Sorry? No, what is written? Temperature. It increases. Okay. What about stagnation pressure? Alright. Yeah. And velocity? Right. And density? Right. Because it's a compression phenomenon. Okay. So there's a question here, but I think it's very easy for you to solve. So let's consider a converging diverging nozzle with an area ratio of 3, and you have to assume that operation is happening with a perfect gas gamma 1.4. Determine the pressure ratios that would cause operation at the first, second and third critical points. So we have discussed the first, second and third critical points, and like I said, the pressure ratio is what determines which state is going to be achieved in the CD nozzle, right? So can you tell me, for this given area ratio, how will you first describe, without giving the answer, how will you approach this problem? How will you tell me the pressure ratio for the first critical point? Anyone? Actually, we have solved one of this type of question in the tutorials as well. Okay, are you all still there? Yeah, please tell me, how will you find the pressure ratio corresponding to the first critical point? No idea? Okay, someone was trying to speak something. Alright, we have a lot more things to go through, so please answer quickly. And also the static pressure ratio. But anyways, how do you do it? Okay, which formula will you use? Yeah, someone said isentropic. That is what I was waiting to hear. So you have to say that. So isentropic relation is what you will use for the first critical, and also for the third critical points, right? So you can also use the isentropic table, or you can use the area Mach relation. So please tell me, for this particular area ratio, what is the pressure ratio for the first and third critical points? You can actually go to the isentropic table, just open the area ratio, and corresponding to this one area ratio, you will have two Mach numbers, isn't it? Are you guys looking into the gas table? Or you can use the formulae that you told me. So just give me the pressure ratio value. No. But maybe you are telling me P1 by P2 instead of P2 by P1. Not P naught by P. Tell me P by P naught. Yeah, receiver by chamber. So in your case, it is, yeah, P by the P receiver by P naught. me the reciprocal. Yeah, that is right. So for the first critical, it's 0.97. And what about the third critical? And how did you do this? Did you use the gas tables or did you use a formula? Isentropic table, yeah. So corresponding to this area ratio, you must have got a subsonic Mach number, and corresponding to that, you have this pressure ratio. Similarly, you will have a supersonic Mach number, and corresponding to that, what is the pressure ratio? In the isentropic table, what is not given? Okay, did you find the Mach number? That is the subsonic Mach number. What about the supersonic Mach number? So run through the isentropic table and see corresponding to some supersonic Mach number, area ratio would be given as 3. This is what ratio? No, Mach number again 0.2 is that supersonic? 2.65. Okay, yeah, fine. And what about the pressure ratio? You give me the reciprocal. Anyways, I think you're close to it. Yeah, check and tell me. Are you getting this? Right. Okay, and what about the second critical? How do you find it? How do you find the pressure ratio so that you operate at the second critical point? Okay, so this is why it was important to know what happens inside the CD nozzle just before the shock. So you just now found what is the Mach number for the third critical? Can you tell me? It was 2.65. Yeah. Okay, so this is the Mach number corresponding to the third critical. Now what is happening at second critical? So everything is exactly same like third critical. So up till this point, just before the shock, you should have Mach number whatever you found, 2.65, right? So I can call this as M1, and you also have the pressure value, the pressure ratio up till here. And after this, you have to use the normal shock table to find the pressure ratio across the shock, and then you can tell me the pressure ratio between the receiver and the chamber. So how do you do this? You will have to give me the receiver pressure ratio by the chamber pressure, which is going to be, the receiver pressure is P2 by P1 multiplied to P1 by P0, and P1 by P0 you just now found is 0.047. Did you understand what I'm doing? Yeah, so can you tell me now the final pressure ratio? You know the Mach number, use normal shock table, find P2 by P1, multiply to this value and tell me PR by PC. 0.37. Just check your calculation again. What is P2 by P1? Is everyone solving? Please take part, do the question. Open your gas tables, or if you can use formulae, use that. You know the Mach number, right? So you can find the pressure ratio. Right. Yeah. So in this case, it is 0.376. Okay, so let's move on to oblique shocks. Right. So in oblique shocks, we've seen whenever the flow is forced to turn into itself. So here you are forcing the flow to actually turn its direction. It was moving horizontal, but now it has to deviate by an angle delta. So a shock is going to get created, an oblique shock. Okay, and the shock angle is what the shock makes with the horizontal, right? Or the not the horizontal. It is the angle that the shock makes with the direction of the initial flow. Okay, so here you can see this chart between the shock angle and the entering Mach number, and I hope you are familiar with the fact that there can be two shocks created. One can be a weak shock, one can be a strong shock corresponding to each Mach number. So is this known, or do I explain this in detail? Any questions? Okay, yeah, this is covered in theory. So now my question to you is, let's say a deviation angle is given. Let's say this delta equal to constant, this particular line is chosen. Okay, and this is the Mach number that I'm looking at. So both these shocks are possible, strong and weak. Which one will actually occur? How do you know that? Why? Why can't the strong one occur? Yeah, so we can say that most of the time, most frequently, weak shocks will occur, right? But sometimes strong shocks can occur depending on the boundary conditions. Yeah, you were saying something? Oh, right, but I don't exactly know in the question what were the conditions given. Okay, okay, so naturally, yeah, it is weak shocks. Okay, maybe it was a problem in the question. Alright, but you know the concept, right? So it's okay. So, like you said, it depends on the boundary conditions whether the strong shock will occur or the weak shock, but most frequently we will get weak shocks. Okay. Yes. Boundary condition, like one of your friends suggested, that if we have to get a strong shock, you have to either change the pressure on the pressure ratios across the shock, right? Yeah, so you'll have to, for example, here, let's say this flow is this wedge is placed inside of wind tunnel. Then you have to specially create a very low pressure area here so that a strong shock should occur. Okay? Okay. That sense. Yes. Can you repeat? Your voice is breaking. Yeah. Yeah. apply this concept of strong shock, weak shock directly to a re-entry vehicle. Firstly, because if you have seen the design of a re-entry vehicle, it's not sharp edged. Yeah, so you don't expect an oblique shock, you expect a bow shock. Okay, and now to specifically answer, detached bow shock, and to specifically answer your question whether it's strong or weak, you tell me, what about a bow shock? Is it strong or weak? Yes, exactly. So that's what I was coming to next. So what happens if the deviation angle is more than the maximum possible angle? So if you go back to this diagram, now let us say we consider this particular line, okay? So in this particular line, there is a particular Mach number, right? So at this Mach number and this value of the deviation angle, I can have an oblique shock. This is the theta max. But what if I change the deviation angle beyond the maximum possible deviation? So here you can see that for a given Mach number, okay, for a given Mach number, I have a well-defined delta max, the maximum deviation angle. But now you have shaped this body such that the deviation is much more than this delta max. So now you cannot get an oblique shock. There is no solution on your shock angle chart. So what you will get is a detached shock. And this detached shock or bow shock, you can treat it like a normal shock towards the center. So it is very, very strong. Okay, this is clear, right? I think you all must be knowing this. Yeah, and in the central region you can treat it as a normal shock, but as you move away from the central region, the strength of the shock is going to continuously change. And then there is a sonic line here. So over here the shock is strong enough so that the supersonic flow on this side is going to convert to a subsonic flow on this side. But here the shocks are weaker and you will get supersonic flows on this side, right? Okay. Yeah. So if an oblique shock is broken down, this is a different question. This is on oblique shocks, not on bow shocks. Okay. So if an oblique shock is broken down into components that are normal and tangent to the wavefront, what can we say about the normal Mach number or the tangential Mach number? Does it increase, decrease, remain constant? Okay, normal Mach number changes, but increases or decreases? It decreases, right? Yeah, okay. I mean, normal Mach number is what? Imagine it was a normal shock. Obviously, Mach number is going to decrease. Fine. What did you say for option 2? It remains same. Okay, see, look at the question. It says careful. This deals with Mach number and not the velocity. Okay, the answer, you're giving an answer decreases. Why? Right. Tangential velocity is constant. And what about the static temperature? What happens to it? Static temperature is increasing. So the sonic speed is increasing. So then the Mach number is supposed to decrease in the tangential direction also. Okay, so the next thing we saw was Prandtl-Meyer flows, and for very weak shocks, I mean, you can see in theory these derivations, but the crux of the matter is if the shock is very, very weak and the flow is deviated by a very small angle delta, you can actually derive these equations which says that the pressure jump across the weak shock is proportional to delta, okay, and the entropy jump across that weak shock is proportional to delta Q. Okay, all this equation is valid when delta is small. Now, what this also tells you is that if the deviation is small, then I can essentially ignore the changes in the entropy, because it is cubic order of this small deviation, and hence we can consider the process as isentropic. And this is what gives the concept of Prandtl-Meyer flows. Now if delta S can be approximated as 0, then I can say that this process is isentropic reversible. Is that correct? If delta S is 0, can I say the process is reversible? Right. And remember, we started with weak shock, which is actually a compression phenomena. But since the phenomena is also reversible, I can also have a expansion phenomenon. And that is why an expansion fan can also be treated as an isentropic process. But this is all in the assumption that delta is small. Okay, so then again from theory these derivations come where the turning angle, so let's say you had this very weak shock and across this the flow has turned slightly. Okay, so this turning angle is called nu, or if there was an expansion fan, again the turning angle is this, and m gives the Mach number, right? So we get this relation, and if you integrate this equation you get this huge equation which is called the Prandtl-Meyer function. And what we do is we make a gas table again called the Prandtl-Meyer table. And how do you make this table? You assume that the initial Mach number is 1. So always I have to start with Mach equal to 1, turn this flow by a certain angle nu to achieve Mach number something, let's say 2, and then I can further turn it by a delta nu to achieve some Mach number, say what is it going to be, more than 2 or less than 2 if it's an expansion fan? Answer? More than 2, yeah, so let's say 3. So for example here we have this question. You are given, see forget the left side of the question. What is given to you is Mach 1. Okay, so this is given, and for this given flow we also know that it is turning by an angle of 12 degree, and you are supposed to find m2. So how do you do that? One way is obviously to go back and put this m1 over here. This is m1 and this is m2, right? So you can put m1, you can put the turning angle and solve this huge cumbersome equation and get m2. Or the other way around is you start with m equal to 1, okay, and you ask yourself, by how much do I need to turn the flow so that I achieve Mach number 2.06, and you will find that the answer is 28 degrees. Okay, so you say from Mach 1 I turn by 28 degrees, so I get Mach 2.06, and then I know that I have to turn it by another 12 degrees. But if I were to start from Mach 1, okay, and turn by a total angle of 28 plus 12, which is 40 degrees, what is the Mach number that I would get? And then you refer this value from the Prandtl-Meyer table. Okay, so can you tell me the answer? Is this concept clear, or is there any doubt about how you use the Prandtl-Meyer table? Yeah, you can. So how do you usually solve these questions? Do you not use the Prandtl-Meyer table? Okay, yeah, so right now what you have is the Prandtl-Meyer table. So tell me the answer. Do you know what is the Prandtl-Meyer table, by the way? Where do you refer the Prandtl-Meyer table? Where are these values given? Is there a separate Prandtl-Meyer table? So remember, we said this process is isentropic. Okay, so if you go to your isentropic tables, you will get one column which either it will say Prandtl-Meyer angle, or it will say this symbol mu, which is the turning angle. So for every Mach number, you will have a turning angle. What that means is, let's say for Mach 2, if you see your table for Mach equal to 2, they would have given a turning angle of 28 degrees. What that means is that if I start from Mach 1, I have to turn it by 28 degrees to come to Mach 2. So what is given to you is the final Mach number. Okay, so now go and see for turning angle 40 degrees, what is the Mach number given. See, it is very important that you learn to use these gas tables. That explains you the utility of making these gas tables in the first place, because otherwise you will have to solve this huge equation. Okay, I don't have any gamma theta angles here, so I don't know what you're referring to. You don't have the tables? Okay, fine. So I'll leave this for you to do later, but I'll give you the answer. It's 2.54. Okay, but I mean, I understand that in NPTEL exams you're given the relevant set of values or relevant information, but you should also know how to look into the gas tables. Okay, it's very important. Yeah. Okay, so maybe you have a different version of the isentropic table. Okay. Yeah. No, so the reason why you expect the answers to match, so you are saying that if I am turning first by 28 and then by 12, the answer should be different from turning directly by 40 because of frictional effects. But what you assume here is that, for each, so this is an expansion fan, but what is an expansion fan made of? Each of these lines are actually sonic lines. Okay, and the assumption comes back, it boils back to this, that delta S is approximately cubic function of the deviation, and the deviation is very small. Now what you are challenging is not this method of calculation, but what you are challenging is this assumption. Can I even assume that delta S is small? Is it small enough? That is what you are asking. So then you have to check your experimental conditions, if the deviations are small or if the frictional effects are significant or not. But usually, okay, from experiments that I have done in my lab, expansion fans, you can trust the gas tables. Shocks, not so much. But then I've done some simple experiments which we do here in our course. Yeah, sure. Okay. Now we solved certain type of questions in the tutorials. We solved this one question if you have seen the YouTube videos or if you have attended that lecture, so there was this reflection problem. An oblique shock was incident on this physical boundary. Okay, so there is a wall over here, and then it reflects. So this is a type of reflection from the physical boundary, and the other type, what you can see here, is reflection from a free boundary. So are you aware of this free boundary concept? Yeah, why are these free boundaries created? Exposure to atmospheric conditions. Okay. Yeah, so these boundaries are created. Yes, go ahead. So you are saying that across the boundary the pressures are different? Okay, so I have this question also. Let's do this before the previous question. So it says you have to, so I have an ambient pressure, okay? I have some ambient pressure, say receiver pressure PR. So you have to tell me about PA, PB, PC, PD and PE and so on. Okay, and what is given here, this is, as you can see, it is an okay, let us assume this is an oblique shock over expansion case. So let's start with oblique shock, and then this oblique shock is going to turn into a expansion fan, like you could see here. Can you tell me what happens? What about PA? PA is more than PR or less than PR? Over expansion case. You answered before. It's the same question. PA is less than PR. Oh yeah, over expansion. And what about PB? So the oblique shock is created so that A jumps to B, and what? How much jump? Sorry? PB, it's an oblique shock. How can PB will be more than PA? Yeah, but is it equal to PR or less than PR? Same question. So you have this free boundary here. What happens to the pressures on either side of the boundary? Why is this boundary being created? Okay, why will the oblique shock occur? What is the purpose of this oblique shock to occur? To increase the pressure to match. Yeah, to increase the pressure to match the ambient condition. Right, so it should match, right? So then PB should be equal to PR, isn't it? Now, but what happens now is that this oblique shock continues. And then if you compare, okay, so let me draw an oblique shock. Now, this was an oblique shock, okay? And this was the other oblique shock. Now, this was A and B. Okay, so across this pressure jumped. But again across this pressure will jump. And now what will happen? PC will be more than PR. But that is not acceptable. So then what will happen now? An expansion fan will be created. Are you following this? Yeah, so now in this region C, expansion fan is going to be created. And then you will get this region D. So what is the purpose of this expansion fan? To reduce the pressure, right? And again match the ambient condition. So again what do I have? PD is equal to PR. And this process keeps continuing until the strength of oblique shocks and expansion fans is negligible. Are Are you understanding this? Yeah. Yeah, no, but then when I asked what happens across the free boundary, first I wanted to know if you understand that the pressures are constant across the free boundary. The free boundary is formed by the shock wave? No, the free boundary is formed because of the shock wave, but the shock wave is not the free boundary. Yeah, so what I'm asking is, why is this free boundary created? It is because there is a certain region between this oblique shock, okay, this region B, which has the same pressure as the receiver. Okay, so this free boundary is created because of this cascading, continuously increasing and decreasing pressures across the shocks and expansion fans. Okay, so coming back to this question, so you have these free boundaries, and another example is when you have the physical boundaries. So the question is, the waves which reflect from physical boundaries, what happens to them, and the waves which reflect from free boundaries, what happens to them? In other words, will the waves which are reflected be of the same family or different family as compared to the incident waves? Did you understand? Yeah. It can be any, right? So if the incident is shock wave, will the reflected be shock wave? So let's take this case first. It would reverse, right? So when I say family, it means, so oblique shock is one family, expansion fan is another family. So if an expansion fan is incident on a physical boundary, what would you expect on reflection? Another expansion fan. Okay. So here I can say it is going to be same family, and here it's going to be different family. And if you have not seen the previous tutorials, go back. We have solved a question for this particular example of reflection. We have also solved, obviously we have solved this free boundary, but we have also solved physical boundary questions. Yes. Why a free boundary establishes? Yeah. So did you understand this shock, and then after the shock an expansion fan is created? Yeah, and in this case I think this was an under expanded nozzle, so first an expansion fan is created, then shocks are created. Okay, so this you can easily understand, isn't it? Yeah, but then you see that this expansion fan, it had to turn somewhere. It had to turn somewhere and become an oblique shock, and this is why these free boundaries are going to be created. So there will be some pressure gradients. Now it will not be here. This is the free boundary. Across this there is no pressure gradient, but as you move from this what is demarcated as region 4, okay, so you have this first line. Across this, now the pressure has started decreasing. Okay, so the pressure at this location is lesser than the ambient pressure. Then again over here it is even lesser. So what is going to happen is that because of these pressure gradients, now the flow is going to turn. Okay, so this reflection is happening because there is a front created. So there is fluid in this region, there is fluid in this region, but a front is, do you understand, a fluid front being created? Front as in imagine a cyclone. So in a cyclone you have so what is a cyclone? It's essentially air, right? But then there is this region of the cyclone, but there's a region where there's no cyclone, and this is called the front. Yeah, so across which there are a lot of jumps in the properties. So here also there are jumps in the properties. So this front is going to get created. Yeah. Okay. So here you don't have huge pressure gradients, right? Yeah. Yeah, so this region is exposed to the atmosphere. This region is the atmosphere. Here there is no pressure difference. This is also a free boundary, or what you would call a slip line. Okay, and this is the free boundary from where the reflection is happening. Here there is a pressure gradient. That is precisely why the reflection is happening. So imagine that there is a thick wall here, a physical boundary. Then there will be reflection, isn't it? So instead of thick wall, now what you have is high density fluid, and here you have low density fluid. Okay. Yeah. Yes. Density or pressure gradient. So it's just not what I was trying to say is the free boundary is going to be created because of these pressure gradients, definitely. But there are regions, this is also a free boundary. This, you cannot forget this slip line. Okay, why is this slip line important? So there is a flow direction. The flow is still having a direction, and here that flow, it doesn't have the fluid over here doesn't have a flow, but the pressure is same. There is no pressure gradient here. Okay. In what? Uh-huh. Okay. Yeah, you can say that it's because of these pressure gradients that the free boundary is created. Yeah, that is correct. Okay. Yeah, but don't see, it is correct, but don't get confused that the pressure gradients exist across all the free boundary. It is in this region that the pressure gradient exists, and that is why the free boundary is created, which is fine. But if I ask you the other way around, is there a pressure gradient across the free boundary always? In this region it is not. Yeah. Okay. Any other questions? No? Okay, so yeah, we'll move on to the next part. So we have solved questions again in the tutorials on supersonic airfoils and also thin plates, right? So there was just one flat plate which was placed at some angle of attack, right? So let's say it is this flat plate and the flow is horizontal. So the flow is forced to turn into itself, right? So here we'll have an oblique shock, and here we'll have an expansion fan. And what happens here at the trailing edge? The flow was parallel to the plate, okay, and now let's say it moves in this direction, so it is going to have an expansion fan, and here we are going to have a oblique shock. Is this clear? Why oblique shock and expansion fan should occur at the top and bottom of the plate. Yeah, this is clear, right? So you should always see whether the flow is being turned into itself or away from itself. Now I have shown you here two diagrams. You can see in the first case, case A, you have a diamond airfoil, okay, and in this case the angle of attack of this airfoil is very small. So what you find is that the flow is at this point from 1 to 3 it is turning into itself, but even from 1 to 2 it is actually turning into itself. You can see that clearly. Yeah, so at low angles of attack you have oblique shocks on both the top and bottom surfaces, whereas in case B, when the angle of attack is high, now from region 1 to 2 what is happening, that the flow is being turned away from itself. So you are going to have an expansion fan over here. So you should be careful about the angle of attack and you should always measure. So for example, you are given a question that the angle of attack is 5 degrees, but the half angle of this diamond airfoil is 15 degrees. So you know that now the flow is being deviated, turned into itself by 10 degrees. Is this concept clear? Why I want to show you this is because usually the picture that is in your mind for diamond airfoils is the bottom one, because we compare it to this thin plate. Any doubts here? No? Okay, so given any of these cases you should be able to solve the questions. Again, refer to the tutorials, we have solved questions of this type. Okay, so this we have already discussed, and okay, so the last parts are the Fano flow and Rayleigh flow. So what is a Fano flow? What is the assumption of Fano flow? We have exceeded time, it's 1.5 hours. Yeah, can someone answer? Sorry, please repeat. No heat transfer, okay. Q is 0. Okay. Viscous flow. So basically, yeah, so we consider losses due to friction. Alright. And then we have this HS diagram. So what is the upper branch corresponding to? The upper branch corresponds to what? Subsonic, and the lower branch corresponds to the supersonic. And what is this limiting point? Yeah, this is the sonic condition. Okay, and how do you define a star reference for Fano flow, or what is called the Fano star point? Where is the Fano star point on this HS diagram? Maximum entropy point, or which is also the limiting point, right? Yeah, so this is what I was pointing to you earlier. If you see, we discussed stagnation point. So from state 1 I go to 1s by isentropic process and achieve Mach 0. Another case was 1 star, where I go isentropically and achieve Mach 1. Okay, this is isentropic. There are other star reference states, which is 1 star Fano flow, where you go by a Fano process, right? So you are going to allow friction, and again you are going to achieve Mach 1, which is the sonic speed. Now, if you remember, we just saw a question. If I start from two different static conditions and I achieve the isentropic star reference states, those isentropic star reference states will be different for those different static conditions, right? But if I start from two different static conditions here on the Fano flow, on the Fano line, I'm going to achieve this sonic point or this star reference point, which is same no matter where I start from. Okay, so whether I start from 2 or 1 or some new point 3, I'm always going to achieve the same point on the HS diagram. Is this clear? Guys, please answer. Is there any doubt about this? Okay, and this point, this concept is important when you are solving questions. So if you have to solve questions for a Fano flow, you're going to use this star reference state, you're going to use Fano tables, and there you should remember that, say for example, you are given P1 by P star. Okay, and let's say you're given P2 by P star. So if it was an isentropic star reference state, P1 star and P2 star would be different. But now that is not the case. In the Fano case, you have P1 star is equal to P2 star for a Fano flow, and similarly for a Rayleigh flow also. And if you have any doubts, we can discuss about the subsonic and supersonic conditions, why velocity increases in a subsonic Fano flow and decreases in a supersonic flow. Any questions about Fano flow? Any conceptual questions? Okay, so you can explain whenever you're revising the concepts, you should be able to explain yourself why any of these quantities is say increasing in subsonic and decreasing in supersonic. Okay, and then what about Rayleigh flow? Rayleigh flow is where heat addition or removal in the system is allowed, but frictional losses are not allowed, right? Yeah, again here we have the upper branch, which is the subsonic branch, and the lower branch, which is the supersonic branch. So let's say we are adding heat to the system. Okay, so you're adding heat to the system. What happens to the temperature? Let's say we have subsonic flow, right? So we have subsonic flow and we are heating, and I'm asking you what happens to the temperature. Sorry? Yeah, I'm asking. So there is heating and it's a subsonic flow. Okay, so you're on the upper branch. My question is, what happens to the temperature? Will the temperature increase or decrease? Always? Okay, so first tell me till where the upper branch is defined. Is it from 1 to 3, 1 to 2, 1 to 4? What is the upper branch? What is the upper branch? Is it till 3 or till 4? Yeah, till 4. And this point 4 is the limiting point, right? It is the point of maximum entropy. What is point 3? Compare point. Yes? Yes, so if I compare point 3 and I compare point 4, so point 3 has higher enthalpy, higher temperature than point 4. So that is why you see this enthalpy can increase and then decrease. So this is very important. You should understand what is happening in a subsonic flow. There is a point of maximum enthalpy, but beyond that what happens? So if you are adding heat, see the velocity was increasing. Okay, so whatever heat you were adding, some part of that energy, it went in increasing the kinetic energy. Okay, so if I write down your equation, your enthalpy, total enthalpy is the enthalpy plus the kinetic energy. Okay, and this total enthalpy is going to increase. The stagnation enthalpy will always increase on heating. So when I add energy by heating, some amount of energy goes in increasing the kinetic energy and the remaining amount goes in increasing the enthalpy. But then there comes a point 3, where the total whatever energy you are adding by heating, that goes completely in raising the kinetic energy. So there is no raise in temperature. And if you go beyond point 3, what happens? You are adding some energy, but now the velocity increase is much more, and hence the extra kinetic energy which is being added has to be revived from the enthalpy. So the enthalpy is going to drop. Okay. Yeah, and similarly for the cooling process. Okay, so if there are no questions, we can end the meeting, but I'll wait till all of you leave. This is what I had for the summary. Yeah. Yes, please. Yeah. Yeah. Yeah, that is why I was trying to make it clear that don't confuse the free boundary with pressure gradient. So there is pressure gradient. Yes, I agree. That is why this reflection is going to happen over here. Okay, but don't confuse free boundary with pressure gradient, because when you solve the flow across a free boundary, you are actually solving this region. Okay, you never solve this region. Yes.